Wait, no, that's not right, is it? Greetings from the New York City College of Technology. Welcome to lecture number 3 of Physics 2. Today, we're going to be talking about not just the electromotive force, but simple circuits, such as circuits that are in series and parallel. Alright, so what is the electromotive force? When we have any circuit, when you have a battery, like one of those batteries from Duracell, you'll always see this positive side colored brown, and then this negative side colored black. Well, what do those actually represent? Well, the thing is, there's a little electric potential difference, also known as voltage, running in this battery. Some of the charge is being pushed to the negative side, some charge is being pushed towards the positive side and away from the negative side. Think of it like a redox reaction. So this force, this voltage, is not created by adding in any new charges. There's no new charge being added. We're just changing around the existing density of charges. We're just rearranging the existing charges to create a potential difference as we move. So when we draw our circuit diagrams, you're going to see this as our battery. This longer line is our positive terminal, and the shorter line is our negative terminal. And you'll see there's this small potential difference in between them. This might have value of electric potential P high, for example, and this one P low, and then the total voltage is just going to be the high minus the low. Pretty simple, right? Alright. Please don't fucking kill me for looking at my notes. Jesus Christ. What the fuck? Okay. So, our basic circuit has these components. So we've already seen the battery part, which is right over here, but now we have this conductive wire, and this wire is transporting a bunch of little charge-carrying particles. And the flow of these particles through one point in the wire at any given point in time is what we call the current. So this is the current, dq dt. How much of this charge is going through this space in some differential time. Alright. So the electric current is always flowing from positive, just like this, and then over to negative. But wait a dang second. What is this in the middle? This is what we call a resistor. Why do we need a resistor?
Otherwise, the circuit will fuse. There will be an overload of current. It's just like if you have
short circuits. Yeah. Oh yeah, I know.
So electricity is bad even for the brain. I'm not talking about phones. I'm talking about the electric chair.
Okay, keep going.
So you can see we need resistors.
Yeah, I know.
You don't want to get electrocuted.
Shut up. Okay. All right. So this is a resistor, and as you can guess by the name, it essentially damps charges' speed. They don't go through it as fast as the rest of the conductive material. Is that correct?
Yeah, essentially, it's kind of analogous to mechanical friction.
Okay. So, for example, imagine you're riding in a car, and if you're riding at a very high speed and you want to brake suddenly, if you immediately go and stop at 0 mph, conservation of momentum is going to screw you over very fast, and you're going to fly through the front windshield for the same reason you don't want to crash your car. So instead, we have these little mechanical damping machines, a spring dashpot system inside our cars, so that whenever our cars abruptly shake if we're not on a well-paved road, or whenever we brake very fast in case of a dangerous emergency, this slows our motion down, eases it out to a reasonable pace. And in the same way, we don't want our current just flowing with no resistance, because electrons flow extremely fast. So this thing is going to short circuit and start burning up, which is really not what we want. So we have to have a resistor in place to stop it from doing that. So that's a simple circuit. So now, how do we calculate the current and resistance of a circuit, especially in total? So now this is the simplest circuit. We've just got one resistor. So the law V equals IR, the law V equals IR holds here. So if we say, for example, there's a potential difference of 10 volts over here, and this is 2 ohms, that means that the current at this specific point is equivalent to 5 amps. 5 amps times 2 volts is 2 ohms is 10 volts. And it turns out, no matter what, since all right, so it turns out when you have any series, we've just got all these resistors damping everything out. There's only one path for the current to go through. It's not like it splits at any intersection. Not like traffic is splitting. Everything is going through one road, and thus that means that the flow of charge has to be the same at every point in time, or every point in space, rather.
See.
Sand?
Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything.